We present Zoom to Learn, Learn to Zoom, where we show that when applying machine learning to digital zoom for photography, it's beneficial to use real, raw sensor data for training. Many times, we're constrained to be physically close to subject we want to see, and need to zoom in images to obtain legibility. For example, when we sit at the back of the classroom and want to read text on a distant projector. Or we want to see through obstructions. Let's assume that we want to zoom in this outline region of the image. Digital zoom, for example, by cubic upsampling, inevitably decreases the quality of the contents, while optical zoom requires a zoom lens that may not be accessible. Traditional super-resolution models are trained under a synthetic setting. These methods synthesize low-resolution images by downsampling from high-resolution targets, producing noise-free low-resolution input. The model then learns to recover the high-resolution target that the input is downsampled from. This limits the model capability to handle noise that is always present in real-world low-resolution images, and the learned models are limited by the input processed images that are often stored 8-bit. Conventionally, images are processed from raw sensor data through an image processing pipeline that consists of a sequence of operations, including demosaicing and denoising. In this paper, we propose a super-resolution approach that leverages the full raw sensor data by training a machine learning model end-to-end using raw sensor data as input. Let's first look at an example. Here, we want to zoom in a region that's distant from our viewing point. If we apply ESR again, the winner of the most recent Perceptual Super-Resolution Challenge PERM, we see that it fails to handle noise and generates false color artifacts around high-frequency regions. In contrast, our zoom model trained with real raw sensor data produces high-quality, super-resolved output. Let's now go through how we enable training our model with raw sensor data as inputs. The question is, how do we get ground truth high-resolution image for raw sensor data? How can we do better than the current best camera image processing pipeline? We propose to capture data with a zoom lens. We use a zoom lens that ranges from 24mm to 240mm to capture sequences of images taken by different focal lengths. Here is an example data pair captured with two different focal lengths: input low-resolution image and output high-resolution image. You might notice that there is a slight perspective change between the foreground and the background between these two images. Interestingly, we found that when the camera moves with a rotational motion during zooming, the lens groups themselves move with a translational motion, leading to a change in the effective camera center, and thus slight misalignment between our training data pairs. In addition, there exists the ambiguity to align images of different resolutions. This brings up the challenge that we cannot apply pixel-wise loss to supervise our model, as we care about pixel-level accuracy. Contextual loss is recently proposed to train unaligned dataset. It treats the target and source images as collections of feature points, and only tries to minimize the distance between the most similar feature pairs, regardless of their spatial location. When we apply contextual loss to train our model, because the feature matching doesn't consider any spatial position of image features, the trained model produces repeating artifacts due to incorrect feature matching between the source and target images. Inspired by the edge-preserving filters in the bilateral space, we encode the spatial information into the contextual loss and are able to train our model to produce artifact-free, super-resolved output. An alternative to capturing raw sensor data is to synthesize raw sensor data. However, a range of real sensor noise characteristics, including crosstalk noise and imperfect fill factor, are challenging to model accurately. Let's now look at some results. We first show a comparison with ESR again, the state-of-the-art super-resolution model. More baseline comparison results can be found in the paper and the supplement. As expected, ESR GAN is not able to handle real-world, low-resolution images that often contain noise. Our model is able to produce better quality output. We also compare against a model trained with synthetic sensor data. We use a standard sensor synthesis model that retains one color channel from a processed image following the Bayer mosaic pattern, and then adding Gaussian noise. Model trained with synthetic sensor data generates color artifacts. Our model trained with real raw sensor data is able to produce better super-resolved image. Here are some more results from our 4x zoom model. We have released our model and dataset. For more details and results, please visit our project website.